I have the BFO oscillator completed, and to test it, if you have an oscilloscope, an easy way to do it is just hook onto the top end of R67, which is the emitter follower transistor that's sending the signal over to the transformer. So if you hook on there, you can see it, and now we'll go over and take a look and see what it looks like on the oscilloscope. We have about 2.7, 2.8 volts output, but boy, you say it sure doesn't look like much of a sine wave. It's at our 11 megahertz, but well, you're right, it doesn't look like much of a sine wave. It's kind of distorted, but in this application it really doesn't make much difference, and let's see why. Here on the spectrum analyzer, I'm sweeping from 0 megahertz at the left, that's the big spike on the very left screen, to 100 megahertz. Each division is worth 10 megahertz. I've put in a nice clean sine wave out of my signal generator at 10 megahertz. So you can see there's not much other activity going on at other frequencies. So if we looked at that with a scope, it would be a nice pure clean sine wave. Let's try something just a little bit different. What I just did is turn my sine wave into a square wave. Square wave is made up of the fundamental frequency, which is at 10 megahertz, and an infinite number of odd harmonics at decreasing amplitudes. So you can see up here, this is at 10 megahertz, 20 megahertz, 30 megahertz. This is the third harmonic. Here's the fifth harmonic, the seventh harmonic, and the ninth harmonic. There's some even harmonic content in there also, but it's way down. So what that is a bunch of different frequencies. If we consider the display of the scope, the sine wave, nice and clean, is a single frequency. The square wave is made up of multiple frequencies, and it doesn't look at all like a sine wave. So anytime we have a distortion from a pure sine wave, there's other frequencies involved. So our BFO signal didn't look nice and clean. It wasn't a nice clean sine wave, so there must be other frequencies involved. So let's take a look at what it looks like on the spectrum analyzer. We're back to 11 megahertz again. Here's our 11 megahertz frequency. Here's the second harmonic, 22 megahertz, third harmonic, 33 megahertz, fourth harmonic, fifth harmonic, and so on. So we see there's a lot of harmonic content. If it was a nice pure sine wave, we'd only have a spike there at the 11 megahertz. Is that a big deal? Well, it all depends. And in our particular application, it isn't a big deal, because remember, the next thing we go through after we generate a sideband is we go through a crystal filter. The crystal filter is going to be tuned around 11 megahertz. It's going to reject every bit of this stuff over here by probably 30, 40, 50 dB or so. So we really don't care about the non-sinusoidal sine wave. We could have even got away if it would have been a square wave, because the crystal filter will remove everything but the fundamental frequency of the oscillator. Okay, so we're back at our BFO output. Like I said, it's not a nice clean sine wave, but we just saw that it really won't make any difference. We have about 2.8 volts there, so we're on to the next step. The next step is to put some modulation in through the mic amplifier and generate a double sideband signal. We want to use a signal generator to inject a signal into the mic amp so that we can test the balanced modulator circuit. So in order to do that, we need to know what level to adjust it to. So what I've done is hooked up my old Bitx, VAR Circuits Bitx, and I'm hooked across the microphone, and we'll just talk into it and see what kind of level we get. We've got 20 millivolts per division there, so I'll key it. Testing 1 2 3 4. Hello. Test 1 2 3 4. Hello. Testing 1 2 3 4. Hello. So looking at that, it looks like we're getting around 40 millivolts peak to peak, and on high modulations we get peaks, we get more. So we'll take a look at putting 20 or 30 millivolts into the circuit and try it that way. The way this circuit works, we have our microphone hooked in here. It's going to amplify the audio, and it's going to be injected into the transformer up here. Coming over from the top, we have the beat frequency oscillator up here that's running at 11 megahertz. So we've already seen that. We looked at this point right here with the oscilloscope. We had 2.7 volts of 11 megahertz coming down to this part of the transformer. So we're going to take the audio, the 11 megahertz, mix them together in the balanced modulator here, and the diodes will eliminate much of the 11 megahertz, and in the meantime it's going to act like mixers do, and it's going to output the sum of the audio frequency plus the 11 megahertz and the difference of the audio frequency and the 11 megahertz. So at this point out here we should see some carrier, but it should be suppressed, and we should also see the upper and lower sidebands. Here's a presentation of the signal we have. This is the carrier. Here in the middle, this is the upper sideband, this is the lower sideband. We're set for a modulation frequency of 1 kilohertz, so we have 1 kilohertz per division. So this is going to be 11 megahertz. This would be 11 megahertz plus 1 kilohertz. This would be 11 megahertz minus 1 kilohertz. We'll adjust it back to the center again. Now what we want to do is adjust the balanced modulator pot and see if we can eliminate some of the carrier. I'm going to adjust the ballast pot and the cap and see if we can reduce that. Remember, if we would have had amplitude modulation, at 100% modulation, the sidebands would be 1/2 the amplitude voltage wise of the carrier. 1/2 the amplitude is about 1/2 the amplitude is 6 dB. So we can see we're probably have about 100% AM modulation signal there right now. So we need to reduce the carrier quite a bit. See, now the carrier's down 15 dB, and that's as low as it wants to go with the pot. So now I'll adjust the phasing capacitor. We adjust it for a minimum. And it's a touchy adjustment. A little bit goes a long ways. I'll readjust the pot. You just have to work back and forth. It's nice with the spectrum analyzer. We'll have to see if we can figure a way to do it with the scope. With the scope, you just adjust with no modulation for minimum carrier out. Okay, so that's down 25 dB there. So I'll go back to the pot, tweak. The last little bit is really touchy. There's a little more, so I'll go back to the capacitor. I'm just barely touching the tuning on these. I've had them adjusted before to where the carrier would totally disappear here, but it's super touchy with both adjustments. This would be nice to have a 10-turn pot here for this balance pot. Although anytime you get, we're close to 30 dB there, and remember the carrier is going to be off the skirt of the crystal filter, so it's going to be attenuated even more. So this is probably good. I'm going to turn the camera off, play with it a little more. See, there's 30 dB down right there. I have 30 millivolts peak to peak going in there. If we go to 40, there's 40, and all that did is it increased my sideband amplitude a little bit. And you see, if I keep going up, what will happen is I'll start getting second harmonic energy. So I'm actually overdriving a little bit right now. So here's the second harmonic of the modulation frequency, here's the third harmonic. But if you look, that's 10, 20, 30, 40, 45 dB down even there. So, and I have, at this point, 10, 20, 30, 35 dB of carrier suppression. Spectrum analyzer is a great tool for doing things like this because it lets you see exactly what's going on. We change the modulation frequency. The sidebands will move out a little further. There's 2K modulation. We take it down the other way. So what happens is the resolution of the spectrum analyzer starts trying to combine the waveforms. There's 500 hertz apart. We'll change the setting here to go to 500 hertz per division. You can see we're still have plenty of good carrier suppression. So that's the way you'd adjust the balance modulator if you had a spectrum analyzer. I don't have an easy way of showing you both screens at once, but if you watch the oscilloscope one, we can tweak and you'll see what happens there. The signal gets larger, and when it gets larger, the carrier gets bigger on the spectrum analyzer. So if we just tweak the two of these till we get a minimum amplitude, and this is the capacitor. This is the resistor, so I'm going to just adjust both of them until I get the minimum amplitude displayed. And at that point, if you watch on the spectrum analyzer here, so I've got about minimum on the scope. I'm getting about minimum on the spectrum analyzer at the same time. So if I just adjust them both for minimum on the scope, and now if I apply my modulation, what we have on the spectrum analyzer, it's not as good as adjusting it the other way, but you can see we're still down around 20 dB, suppressed by 20 dB. So, and if we also look, the sideband harmonics are down 10, 20, 30, 40 dB down. So you can adjust it that way. With it adjusted by that method, now I've got about 80 millivolts of upper and lower sideband plus the suppressed carrier on the scope. Let's take the modulation away and measure it now. I take the modulation away, I've got about maybe 8 millivolts. We might be able to tweak that just a little bit better. Maybe not. It's real touchy. Should have stuck with the 8 millivolts, it looks like. That's what I've found when you start adjusting these. Sometimes you hit a point where you just don't get it any better, and you keep trying because you've seen it better. There's our 8 millivolts back. Using this, we can calculate out our carrier suppression. We had 80 millivolts with modulation, and we had 8 millivolts without it. So that'd be 80 divided by 10. Gives me 8, except it was 80 divided by 8 millivolts, 80 millivolts with modulation, 8 millivolts without. So that's 10. The log of 10 is 1, so we multiply 1 times 20. So using this method, just using the scope, I got 20 dB of carrier suppression. By the time you ran that to the filter, it would be suppressed another 10, 15, 20 dB. So this method, if this is all you have, this method will work. I've got the scope hooked up right now on the output of the IF amplifiers, right at the input to the crystal filter. So right in on pin 2 of X4 is where I'm connected. Now, you could also do this same adjustment clear all the way out on the linear amplifier output. If you did that, you'd have a lot more voltage there, but just be careful, don't run it for too long when you're putting out a fair amount of carrier, because you could overheat the output devices. We could test the gain of the amplifier that feeds the filter network by injecting the signal, and here we're injecting, we have 5 millivolts per division. We have about 18 millivolts going in, and we'll go over and hook up to the output of that circuit, and coming out we have about 150 millivolts. So we can take 150 millivolts divided by 18. That gives us 8.3333. If we take the log of 8.3333, it's equal to 0.920. We multiply that times 20, and we get 18.41 dB. And if you look on your schematic, they specify these amplifiers as 18.5 dB a gain. That looks real close to me. If we go into receive mode while we're injecting the signal, we'll turn it up, volume up a little bit. What you hear, let's turn it down a little bit more. What you hear is the 11 megahertz we're injecting. It's going in and it's beating against the beat frequency oscillator, which is just a little off of 11 megahertz, and what you hear is the resultant. If we turn it back up and we go over and adjust the frequency adjust for the beat frequency oscillator, I think this is the right one here. We hear the difference frequency change. So we had a single sideband signal coming in right now, we would work perfectly well and we'd be able to hear it. That pretty much does our balanced modulator section. The next section we need to work on will be the crystal filter. So, till the next video, have fun building yours. Take your time, do it right the first time so you don't have to troubleshoot it.